Okay, so hi all, good evening and welcome back to the 7th week of TA live sessions for AI SMPS. Before we begin, can you just confirm if I'm audible and is my screen clearly visible? Yeah, can anyone just confirm if I'm audible? Okay, thanks for that, Shri. So yeah, today we'll be discussing some questions from week 7. Uh, so week 7 covers basically several strategies or methods to solve different game strategy resolving problems. Okay, so we'll have a look at alpha beta, and we'll have a look at SSS star, min max, several such topics covered in the week 7 content of the course. And yeah, without further ado, I think we can get started. Okay, so let's look at questions 1 and 2 first. So these will deal with the alpha beta algorithm that you may have seen in the course, and there's a reason I have put these two separately, specifically because understanding this will be crucial to solving a particular problem that we'll solve later on in the live session using the alpha beta algorithm. Okay, so yeah, so this is the first question. You're given the pseudocode for the alpha beta algorithm, and the question asks that in the alpha beta algorithm, list the line numbers where alpha cutoff and beta cutoff occur respectively. Okay, so you see a line number beside the each of the lines in the pseudocode, and you just have to tell me the line where alpha cutoff occurs and the line where beta cutoff occurs. Okay, and don't worry if you are not entirely familiar with what a beta and alpha cutoff are, because we will be going through a step-by-step solution involving alpha beta algorithm for a particular problem, particular game tree later on in the live session. Okay, so for now just focus on understanding where alpha cutoff is happening and where beta cutoff is happening. So yeah, any possible solutions, guesses about what will be the correct answer? Okay, so I have highlighted two specific parts, okay, where the cutoffs are happening. Okay, and the condition for cutoff will always be the same, that is when alpha greater than equals to beta, then we will have a cutoff. Whether this is an alpha cutoff or a beta cutoff depends on the node that we are inspecting. Okay, so if this is a max node, okay, then we will apply a beta cutoff, and if it's a min node, we will have a alpha cutoff. Okay, so this means that the beta cutoff is occurring at line 6 and an alpha cutoff is occurring at line 11. Okay, let's go back and verify our solution. Okay, so this also says that an alpha cutoff is happening at line 11, okay, which is what we just saw, and a beta cut is happening at line number 6. Hi, can you please mute yourself? Thanks. Okay, any doubts on this question? I hope this was clear. It's a straightforward question. Okay, that's great. Then let's move ahead to the next solution or next question. So here we are given 4 game trees. Okay, so it's a 2-player game. Okay, and it shows different possible strategies. and we assume that the root node is a max node. Okay, this is an assumption we make about this problem and about several problems we'll see later on in the in the current week. Okay, and we have to choose which of these game trees are actually possible valid game strategies for the root node. Okay, so what do you think will be the answer in this case? D. Okay, so D is one possible answer. Is that the only answer? And is that the correct answer? Think about it. So remember, one hint that you may follow to see if a strategy is ideally correct or not is that whenever we encounter a max node, we select one of its children. Okay, whenever we encounter a min node which is marked by a circle and a max node is marked by a square. Okay, so whenever we encounter a max node, we select one of its children. Whenever we encounter a min node, we select all of its children. Okay, according to this hint, which of these game trees do you think is correct? Okay, so let's have a look at game tree A. So here we are selecting one possible child of the max node. Okay, it's correct till now, but in the second step we select only one child of the min node, which is incorrect. We should have also selected this other child, right? So game tree A cannot be correct. Let's look at game tree B. We select one child of max node, both children of min node, then again one child each of the max node, and both children of the min node. Okay, so game tree B is a correct strategy. Similarly, game tree C is also depicting a valid game tree. Right? So game tree C is correct, and again game tree D is also incorrect because here we are selecting all children of max node where we should have selected only one of the children of max node. Okay, so let's go back and verify, and our assumption was correct. Game tree B and C are the possible game strategies for the root node, which is the max node. So this is you could say something like an assumption that we have followed or set for developing game strategies or game trees. Okay, so whenever we encounter a max node, we will select all of one of its children. Whenever we encounter a min node, we'll select all of its children. Okay, for an in-depth explanation of why that happens, I would recommend you to revisit the lecture videos. I think where professor would have given a much more nuanced explanation of why that might be happening. Okay, although make a note that this is in general the trend, but there are some exceptions to this rule which we adopt in specific methods. Okay, so one such example is the SSS star method, and we'll see what exactly is the difference that we encounter in the SSS star method. Okay, but for now this is an assumption that we make, and always stick to that. Okay, cool then. So I think this should be clear. Let's move on to the next question, which is questions 3 to 5. Now we will deal with filling up actual game trees. Okay, so here in question 3 we are shown a game tree with evaluations win, loss or a draw, again from a max perspective. Okay, so we will again assume that the root node is a max. Okay, in this game tree P, Q, R and S, which are shown in the figure over here, these indicate different strategies or moves at the level of the root node. Okay, then we have to decide what will be the final outcome of the game when both players play perfectly. Okay, so I'll let you think about this and then we'll have a look at the solution. You can make an assumption here that W or a win, you can make an assumption that win will fetch you +1 points, a loss will fetch you -1 points, whereas a draw will fetch you 0 points. Okay, so based on that you may want to fill up this game tree. Remember that the circle is a min node and a square is a max node. As the name suggests, a circle will try to choose the minimum possible value from amongst its children, whereas a max node will try to choose the maximum possible value from amongst its children. Okay, any answers, any guesses, partial solutions? Okay, let's try to fill in the tree and see what happens. So here the first node that we are encountering is a min node, and it has 3 children, all of which have W or win, right? So it has to choose from +1 +1 +1, so it will choose a win. Okay, now this is a max node. Okay, this will try to choose a maximum value available, so it will choose from draw, win or loss. It will choose a win, right? Next, let's look at this particular node. So this has to choose the least among its children. It will choose a loss. And again, this max node has to choose between loss and a loss, so it will go for a loss, right? Because these are the only options available to it. Now this is a min node. It has options to choose between win, draw and loss. It will choose a loss. Okay, let's fill up the rest of the tree similarly. So this has to choose between a draw and a win, and it is a min node, so it will choose a draw because 0 is less than +1, right? And this is a max node, so this will try to maximize and it will go for a win. This is a min node, so it will go for a loss. This will also go for a loss, but this max node will try to choose the best among -1, 0 and -1, so it will go for a draw. Okay, and then this is a min node which has to choose between win, win and draw, so it will go for a draw. This again is a min node, so it will go for a draw. This will go for a win, this will go for a win again, this will go for a loss, this will go for a loss. And let's have a look at this node. This will go for a draw, this will go for a win, this will go for a win. Sorry, this should have gotten a win, right? So please correct me if I'm making any mistakes. Okay, I am also prone to making mistake. This will be a win instead, right? I hope that was clear. Okay, so we were here, this has a win, and let's fill in the rest of it. So this will choose a loss, this will choose a win, this will choose a win again, and this will choose a draw. So finally this will choose a win, right? Because it has to choose between loss, draw, win and draw. So any doubts in how we filled up the game tree? Okay, if not, then great. Let's verify our solution. Okay, so the third question asked us what will be the outcome of the game when both players play perfectly, and that will be a win, which we just saw, which is the value that the root node attained after we filled out the whole game tree. And the fourth question, which is also based on the same problem, asked us which of the moves are the best moves for max, and the answer would be R, right? Because that is the only strategy that is leading it to a win, right? R is the only one that is leading it to a win. Q and S are leading it to draws, whereas strategy P is leading it to loss. Okay, so the best move is R, best strategy is R, and then which of these lead to a draw? That would be Q and S that we just saw. Okay, so any doubts in this question, this couple of questions 3 to 5 that we just solved? Okay, if not, then that's great. Let's move ahead to the sixth question then. Okay, so for question 6 onwards we will be using this same game tree. Okay, so this game tree that you see over here in the figure, it shows a 4-ply game tree, right, with evaluation functions values at the horizon, right? So the leaf nodes at the bottom of the tree, right, which are labeled as 1 2 3 4 up to 24, these are the horizon nodes or the leaf nodes. Okay, they carry reference numbers, okay, at the bottom, which we just saw, which are 1 2 3, and some values assigned to them, which are the 64 80 69 so on and so forth, right? Whenever necessary we can assume a top down and left to right node order, okay, and we have to use this game tree to answer the next few questions. Okay, so don't worry about the instructions now. These will become clearer as we look at the solution or the question statement itself. Okay, so the first problem that we are going to solve, or the first method that we are going to use to solve this particular game tree, is the min-max strategy. Okay, and that will be similar to what we just did in the case of the win, loss and draw problem that we encountered a few minutes ago. Okay, so similarly we have to fill out the rest of this game tree, just that instead of win, loss and draw, here we have actual numbers or integers. Okay, so I will let you try to solve it on your own before we can discuss the solution. Okay, let's try to solve it then. Okay, so this is a min node, right? So it will also choose the minimum among 64 and 80. So this will get 64, right? This is also a min node which will choose between 69 and 68. So it will choose 68. And then this is a max node, so it will choose 68, which is the greater one among 68 and 64. Okay, similarly we'll fill the rest of the subtrees as well. This will be 72 because it's the minimum among 90 and 72. This will be 16 because it's a min node. This will be 72 because the maximum among 72 and 16, and then this min node will have the minimum among 68 and 72, which is 68. Any doubts up till this point? Okay, that's great. Let's solve the rest of it as well. So this will choose 17, this will choose 13, and this will choose 17, right? Please correct me if I am making any mistakes along the way. Please feel free to unmute yourself and let me know. Okay, so this will be 58, this will be 57, sorry about that, and then this will be 58, sorry about that, and then this will be 17 again because this is a min node. Okay, now similarly this will be 62, this will be 31, this will be 62, this will be 11, this will be 36, this will be 36, and this will be 36 again, and then this will finally be 68. So have we arrived at the correct solution? Is any doubts up till this point? Okay, if not, then that's great. Let's go back to our question and see what the question asked us. Okay, so the question asked us to apply the min max value, apply the min max strategy and tell and report the min max value of the game. So that will be 68. Okay, which is again the value at the root node once we solve the whole game tree. And then we had to list the nodes or the node reference numbers in the best strategy. So let's go back to our filled up game tree. So this is the min max value 68. Okay, now let's look at where the 68 is coming from. It's coming from this min node. Okay, this min node 68 is again coming from comparing this 68 with this 72. Okay, this 68 is coming from this min node, that in turn comes from comparing 69 and 68, which are nodes 3 and 4, and this 72 comes from this min node over here, that comes from comparing nodes 5 and 6, which contain 90 and 72. So the nodes that are contributing towards this final 68 would be 3, 4, 5 and 6. Okay, let's have a look at the solution, and that is what is given to us. So the min max strategy, min max value is 68, and the nodes in the best strategy are 3, 4, 5 and 6. Any doubts here? Sorry Satish, can you come again? Yeah, you're audible. Yeah, it's audible. Please go ahead. Yeah, you could say that. Although I would also request you to verify this with the lecture videos once. Yeah. Yeah, that's true. That's true. Yeah. So I think you're correct. Just verify this with the lecture videos or notes once. Yeah. Okay. Anything else in this question? Okay. That's great then. Thanks for confirming. Let's move on to the next question. Now comes the alpha beta algorithm. Okay. So now it's the same game tree that we saw in the previous question when we applied the min max strategy, but the difference is that here we have to apply the alpha beta algorithm. Okay. And we also have to be aware that this might involve making some alpha cuts and beta cuts, and a single cut may remove a bunch of edges at once. Okay. Or a whole subtree at once. We'll see examples of that as we try to solve it. Yeah. Mm-hmm. So it was chosen based on the min max strategy. So the circles represent a min node and the squares represent a max node. So when we are trying to fill a number for a min node, we will choose the minimum value from amongst its children. Okay. And when we are trying to fill in the value for a max node, we will try to choose the maximum from amongst its children. Mm-hmm. That's right. That's right. Mm-hmm. So we got this 68 from comparing this 68 with this 72, right? So we also have to include this 72 in our best strategy. Yeah? And this 72 in turn comes from this 72, which again in turn comes from 90, comparing 90 and 72. Um, so I think this in turn was what was asked by your colleague Satish, right? Since we are using a 4-ply game strategy, we will report the best four of them, or the four of the most relevant four of the nodes that gave us the best strategy. They are the best. Yeah, no problem. It's a important question actually. So the most relevant nodes. So if we think about it, in fact, all of these nodes have contributed to get this 68, but the most relevant ones are these four. Okay, thank. Mm-hmm. Okay, this one. Okay. Mm-hmm. This one. Mm-hmm. Right. So this is where this is what I was talking about. We choose the most four relevant nodes that give us the best strategy. Yeah. So all 24 of these actually contribute to us deciding that 68 is the final value. But we can't include all of them. So we choose the two that gave us this 68 and this 72. That in turn gave us this 68 and this gave us the final 68. Okay. Okay then. Anything else before we move on to alpha beta? Okay, let's move on to alpha beta then. So here we have to apply alpha beta, and before we do that, let's revisit the alpha beta pseudocode once, just so that we are aware. Okay, so what the pseudocode tells us is that if we arrive, so for a given node n having a alpha value of alpha and a beta value of beta, this is the code flow that we have to follow. Okay, if n is a terminal node, which is a leaf node, then we return the value of n, or the evaluated value of n, which is given in the contained within those boxes or circles. Okay, in our case boxes only, because the leaf nodes are all max nodes. Okay, if n is a max node, for each child of n, okay, we will recursively apply, or we will apply an alpha value which will be the maximum of the current alpha, and a recursively applied alpha beta algorithm to the child of that particular node. Okay, if alpha happens to be greater than equal to beta, then we apply a beta cutoff and return beta. Okay, otherwise we always return an alpha value in case of a max node. In case of a min node, again we follow a similar strategy, just that instead of max we have min over here, and again if alpha happens to be greater than beta, we apply an alpha cutoff, return an alpha value, otherwise we always return a beta value in case of a min node. Okay, so I just wanted to go through this to make you familiar. Let's now proceed to solve this method using the alpha beta strategy. Okay, so first what we have to do is we have to initialize the alpha and beta values. Okay, so let's initialize alpha as minus infinity and beta as plus infinity. So remember, in the pseudocode we were assigning and returning in usual cases a beta value for a min node, right? And in case of a max node, we were assigning and returning an alpha value for the max node. Okay, now that we have initialized these values, let's try to move it down to the children of this particular node. Okay, so this was for this max node. Next, this max node will pass it on to its children, or the leftmost child first. Okay, not all children. So this will get passed on to this child, which will have minus infinity and plus infinity. This in turn will pass it down to this one, which will have minus infinity and plus infinity. I'm not writing alpha and beta again and again. You can assume that the top one is alpha and the bottom one is beta. Okay, and this again will have minus infinity and plus infinity. This will pass it down to this 64 horizon node. Okay, now this has been evaluated to have a value of 64, and this is a min node. Okay, so what changes will now happen? Remember, it's a min node. Okay, and it's also a terminal node, so it will return a the leaf node is a terminal node, and the node we immediately above the terminal node is a min node. It will inspect the beta value, right? It will choose the minimum of its current beta and the beta that its children has to offer. So its current beta value is infinity, and the beta value that its child has to offer, first child has to offer, is 64, and 64 is lesser than infinity. So we update the beta value to 64. Is it clear up till this point? Okay, I am assuming it's clear. Okay, so now that this set of alpha and beta values for this min node has been updated, it will now pass on this set of alpha and beta values when it looks at its 80 child. Okay, so again this 80 child will return a value of 80. Okay, and this will be compared with the beta value of this min node. So 80 is greater than 64. Okay, so no change will happen to the beta value because 64 is lesser than 80 and the minimum of 64 and 80. Okay, so now that we have inspected all the children of this particular min node, it will be assigned a value of 64. Okay, and this in turn will be passed on to its parent, okay, which is a max node. Okay, and this will compare its alpha value with the value of this child that it is taking an evaluation from. Okay, so this min node will offer a value of 64, and this max node, which has a current alpha value of minus infinity, is lower than 64. Okay, so its alpha value will get updated and become 64. Okay, clear up till this point? Okay, then let's solve the rest of the game tree in a similar manner. So this max node, remember, is not completely solved yet because its second child is yet to be filled in. Okay, so this will pass on 64 and infinity to this child. Okay, and this in turn will then look at this 69 child that it has. Okay, this 69 child will offer a value of 69, which is lesser than infinity. So what will happen? So beta value will get updated to 69. Okay, now this will now look at the 68 child. Okay, the 68 child will offer a value of 68, which is again lesser than 69. So again beta value will get updated to 68, sorry. Okay, so this will return a value of 68, and 68 will get assigned to this min node. Okay, clear up till this point? Okay, I'm assuming it's clear. So I'm purposefully moving a bit slow for this alpha beta method because it can get a bit confusing to solve. So please feel free to ask me to repeat at any point of time. Okay, so now that we have filled up the 64 and 68 values, the 68 now will get passed on or will be offered to its parent. Okay, which is a max node. Okay, this will compare it with its current alpha value, which is 64, and see that it is greater than 64. So its alpha value will get updated to 68, and we will put 68 in this max node. Okay, now that this has been solved, this will now offer 68 to this min node. Okay, this min node again has beta value infinity, which is greater than 68, or 68 is lesser than infinity. So its beta value will get updated to 68, and this will then pass on this set of alpha and beta values to its children. So this will get minus infinity and 68, this will get minus infinity and 68. Okay, now this is a min node, and this will compare it with its immediate child, which is 90. Okay, so this 90 child will offer a value of 90, but 90 is greater than 68, right? So we will not update the beta value. Similarly, the 72 child is also going to offer a value of 72, which is again greater than the current beta value, which is 68. So we will let the beta value remain 68. Okay, and then this node will also get a value of 68. Okay, clear up till this point? Okay, so I'm assuming it's clear. Okay, now that we have put in a value of 68 in this node, this 68 will then be offered to its parent, which is a max node. Okay, and this will compare it with its alpha value, which is minus infinity. Now 68 is greater than minus infinity, so it will update its alpha value to 68. Now can you notice any specific thing happening as per the alpha beta algorithm? Has any specific condition been met? Uh, that's right. That's right. So yeah, we haven't yet filled in the. Let me point to it. We haven't yet filled in this particular min node with 68 value, but because in this set alpha is equal to beta, the cutoff condition has been met, which is that alpha has to be greater than beta. Whenever this situation occurs, we will make a cut. Okay, and here we see that alpha is equal to beta, so we will do a cut. Okay, and we will cut this part of the game tree. Okay, let me mark this. This basically means that there is no purpose exploring this part of the game tree. And can anyone tell me what kind of cutoff will this be? That's right, it will be a beta cutoff because we were at a max node, right? And again, if we go back to the pseudocode, whenever we are at a max node, if the cutoff condition is met, we will have a beta cutoff and the beta value will be returned. So we will do exactly that. We will return the beta value. Okay, so this will take 68. Okay, and this will also pass on 68 to its parent, which is a min node, and this already has a beta value of 68. Okay, so there will be no change to the beta value. This will remain 68 and we will put a value of 68 in this min node. Okay, is it clear until this point? Okay, then that's great. Let's continue solving it then. So this will then pass on a value of 68 to its parent, which is this max node. Okay, and this will then compare it with the alpha value that it currently has, which is minus infinity, which is less than 68. So it will update its alpha value from minus infinity to 68, and this will then be passed on 68 and infinity, 68 and infinity, and again 68 and infinity. Now this min node will look at its child, which is 17. Okay, this 17 will be offered to this min node, and this has a value lesser than its current beta value, which is infinity. So beta will be updated to 17. Okay, will there be a cutoff again? That's right, there will be an alpha cutoff. In this case, again, the condition for cutoff is being met, which is common across alpha and beta cutoff, But since here we have a min node at hand where the cutoff is happening, right, this will be called a alpha cutoff and the alpha value will be returned, right? So this will have a value of 68 as well. And let me use a different color. This part of the subtree will be cut off, and this will be an alpha cutoff. Okay, and then this min node, which has a value of 68, this will offer this information to its max parent, which already has an alpha value of 68, right? So no change will happen to its alpha and beta set. Okay, this will in turn pass on this set 68 and infinity to its next min child. Okay, is it clear until this point? No, so here remember a cutoff happened. So let me go back to the pseudocode. So whenever in a min node a cutoff happens, we return the alpha value. In general, we return a beta value for a min node, but in case a cutoff happens, we return an alpha value, which is where alpha cutoff happens. And here the alpha value was 68. That's why 68 was returned. Okay. Okay. Any other doubts till now? Okay, that's cool then. Then let's keep solving. So again, we were at this particular min node with an alpha and beta value of 68 and infinity. Okay. So this will then get offered a value from its child, which is 13. So 13 will be offered. 13 is lesser than the current beta value of infinity. So this will then get updated to 13. And again an alpha cutoff will happen because 68, which is alpha value, is greater than 13, which is the beta value. Okay, and 68 will be returned again, and we will have a alpha cutoff over here again. And then these will in turn, this 68 will also be offered to its max parent, which already has an alpha value of 68. So alpha value will remain the same. This will be 68 again. Okay, now this 68 will be offered to its min parent. Okay, this min parent has a beta value of infinity, which is lesser than 68, which is what is being offered by this max child, right? So this beta value will get updated to 68. Okay, again a cutoff condition has been met. Alpha is equal to beta. Okay, and once again it's an alpha cutoff because we were at a min node. In this case, we will prune out this whole subtree. Okay, so we are essentially cutting off this branch, but by because we are cutting off this branch, all its descendants are also being cut off. Okay, so we applied one more alpha cutoff over here, and again this will also have a value of 68, which will again be offered to its max parent, which already has a value of 68 in its alpha, so it will remain the same. Okay, and this will then offer its value of alpha and beta to this particular min child. Sorry, alpha and beta. So 68 and alpha will be going to here, going over here, then again 68 and alpha, again 68 and alpha, and again a similar situation will happen, right? So this 62 child will offer a value of 62, which is lesser than infinity. So beta will get updated to 62. Again, the cutoff condition is satisfied. 68 is greater than 62. So this will get a value of 68. And this part will be cutoff. Again, an alpha cutoff. This will again offer a value of 68 to this max node, which already has an alpha value of 68, so no change will happen. This will again pass down 68 and infinity. This 31 node will offer 31, that will update the beta value from infinity to 31. Again a cutoff will happen because 68 is greater than 31. This will also have 68, and like in the previous example, this will again be cutoff, and this will also be an alpha cutoff. Now this will again offer a value of 68 to this max node. Okay, this max node already has a 68 in its alpha, so no change will happen. This will get assigned 68, and then this 68 will be offered to its min parent, which has a beta value of infinity. So again this will get updated to 68, and again the cutoff condition is satisfied. So this whole subtree will be pruned out or cut off again by a alpha cutoff. Okay, and then this node will have a value of 68, which will again be offered to its max parent, which has an alpha value of 68, so no change will happen, and all its children have now been evaluated, so this will be assigned a value of 68 again. Okay, so now we have solved the same game tree using the alpha beta algorithm. Any doubts in the steps that we took to arrive at this solution? Okay, if not, then that is great. So I would also like to point you to this particular resource. Okay, so this is the same game tree. Okay, the solution to the game tree using the alpha beta algorithm. The difference is that instead of marking alpha and beta at each specific node, here we have provided a trace that we would have gotten had we written a program to implement this. Okay, so this has been prepared by Bhaskaran sir, and I am grateful that he has shared this with us, and I am able to share this with you in turn. This document is uploaded to the same folder in which every live session every live session's question answer slides are uploaded. Okay, so if you go to that folder, you will find this document as well, and you can have a look at it at your own free time, or even now, up to you. So here you will find the detailed step-by-step solution. Okay, so the difference, there is a slight difference in notation. Here we have named each level of node as A and the number of node that we are encountering. Let me just depict what is happening there. So we have given this first level A and the first node in the first level as a name of A1. Okay, the second level has been given a name B, so this is B1, which is the first node in second level, B2 second node in B level, and then B3. Similarly, so we have C1, C2, C3, C4, C5 and C6. The next level is named with D, so D1, D2, D3 up to whatever, D12 I think, and all the last nodes or the leaf nodes are labeled with an E, E1, E2 up to E24. Okay, now coming back to our trace. So here you see that we first visit A1, which is the root node, which is the max node, and it has an alpha and beta value of minus infinity and a beta value of plus infinity. Okay, after visiting A01, which is the root node, we visit B01. Okay, which is this min node over here. Okay, B0 is the min node, and it gets the alpha and beta value that were given to it by its parent, which is minus infinity to plus infinity. Okay, after B1 we visit C1. Okay, which is this particular max node. Okay, and we proceed in a similar fashion to what we just saw on the Jamboard. And if we follow it step by step, we solve some leaves, we apply some cutoffs, and finally we arrive at a solution, which is 68. Okay, so I just wanted to point you to this particular resource so that those of you who are more interested in the implementation level details or what exactly is happening at each specific step may have a look at this particular trace. Okay, so now that we have solved it using the alpha beta algorithm, let's have a look at the question. What is the number of alpha cuts and beta cuts? Okay, the question asked us how many beta cuts and alpha cuts are happening, and we saw that there was 1 beta cut and 6 alpha cuts that we encountered. Okay, which is what is also reported over here. Okay, any doubts again in this particular method before we move on to the next method? Okay, then that's great. Let's move on to the next question. Okay, so what the next question, again we are working with the same game tree. This question asks us what are the total number of strategies in this game tree. Okay, remember I told you something about strategies at the beginning. Okay, so yeah, I'll give you some time and you can think of a solution and let me know. Okay, so we have a couple of solutions in the chat box. Let's have a look at how to arrive at this particular answer. Let me clear this out. Okay, so when we are selecting a strategy, remember that earlier we had discussed, when we were looking at some possible game trees, we said that when we are at a max node, we select one of its children. When we are at a min node, we select both of its children. Okay, so following that strategy, let us select this particular child of this max node. Okay, then we'll select all children of this min node, and then we'll select one child of its of the max node. Let us say that we select the leftmost child in both cases, and then min node will select all its children. Okay, so this could be one strategy. Another strategy could have been if we had selected this one instead, right? Similarly, another strategy could have been if we had selected this one and this one, right? This is also a different strategy. Or another strategy could have been if we had selected this one instead, right? So for this subtree alone, just for this part of the game tree, how many strategies did we encounter? So we saw 4 strategies over here, right? One was, let me use different colors to label it. So the main choice is being dependent at this level, right? If we choose this and this, that is one strategy. If we choose this and this, that is another strategy. If we choose this and this, that is another strategy. And if we choose this and this, that is another strategy. So a total of 4 strategies for this subtree alone. Similarly, for this subtree we will have 4 strategies, and for this subtree also we will have 4 strategies. So a total of 12 strategies are possible in this game tree. Okay, I hope that was clear. So for this particular question, we are not really using the property that it's a 4-ply tree, right? We are just looking at what are the possible ways we can take as we traverse down the game tree. So when we are at the max node, the root node, we could have chosen either one of its children, right? We chose to go with initially the leftmost child, and then we, as we went down, we saw that there are 4 possible strategies that we could choose from, right? There could have been a number of other min nodes at the second level, right? We could have had something like this as well, something like this as well, and in turn this could have also had something like this, in which case the number of strategies per game tree would change. Does that answer your question? Mm-hmm. Hmm. That is, yeah, that seems to make sense. But I will also request you to verify this with some other game trees as well. Okay, so this is an example game tree. You might have come across a slightly different game tree in the lecture videos, right? Or maybe in the practice assignment that is there for this week. So you can try to solve that game tree also using alpha beta, as well as try to figure out how many strategies are there, and then see if this trend is still being maintained. Yeah, yeah. Mm-hmm. Mm-hmm. Uh-huh. Sure. Thanks for pointing that out and sharing your observation. Okay, then. So let's look at the solution. So, which is correct? We found 12 strategies. And let's move on to the next question. So, in this case, we are going to apply the SSS star method now. And before we do that, we are going to decide the initial clusters. Okay. So what those initial clusters refer to, for that I would again request you to go back to the lecture videos, but implementation wise, or uh, looking into how exactly we arrive at the initial clusters, we'll have a look at that when we solve the SSS star method in detail. But for now, let's try to find an intuitive way to see the initial clusters of the SSS star method. Okay, and remember I had mentioned one statement at the beginning of the live session, that there is an exception to how we decide strategies, or uh, equivalent of strategies in case of the SSS star method, right? The difference here is that instead of choosing only one child in case of a max node, here we choose all children of the max node and only one child of the min node. We fix that we choose only the leftmost child of the min node. Okay, so we reverse everything, reverse the way we were calculating the strategies or finding the strategies in till now, and we use this way to find the initial cluster. So I would urge you to try to do that with this game tree right now and tell me which of these horizon nodes form the initial clusters. um, yeah, so thanks for your question. So I'm afraid getting into details. Uh-huh. So I can give you an intuition of why we choose to move from, let's say, something like a min max to an alpha beta to an SSS star. Okay, but I would prefer to go into a step by step solution using an SSS star method rather than a detailed explanation of what exactly does the method entail. Ha. Sure, sure. So we'll look at the step-by-step solution in the coming question. But before that, I'll just give an intuition. So if you remember, in the min-max method, we explored the whole game tree, right? We explored each and every node that was present in the game tree. And like we have seen in the previous live sessions, that we won't always have such a good game tree given to us where we have only a few nodes that we can fill in manually, right? In practical applications, we might have thousands and millions of nodes and limited resources to compute our final solution to the game tree, right? In those cases, we would want a slightly more efficient way to arrive at the solution than min max, which explores each and every node. Okay, so alpha beta is an improvement over min max in that respect, that it prunes out certain portions or certain subtrees of the game tree that it seems that it finds to be non useful to us as we move through the solution. Okay, For example, when we apply a cutoff, we know that the subtree that we are going to prune as a result of the cutoff is not going to give us the final solution. Okay, so there is no point exploring that further, so it prunes off that particular subtree. SSS star goes one step ahead in terms of pruning and takes more harsh decisions on which parts of the game tree it wants to prune. Okay, so you could say that there is a stepping up in terms of efficiency as we move from min max to alpha beta to SSS star. This is the intuition behind why we apply these methods. But yeah, we will look at the step-by-step solution as we move to the next question. Does that answer your question to some extent? Okay, thanks for that. Okay then, any answers to what the initial clusters will be? So let's apply the strategy or the approach we just discussed. Instead of selecting one possible solution or one possible child of the max node, let's select all of them. Okay, and we'll select only one child of the min node, the leftmost child alone. Okay, again all children of the max nodes, and the leftmost child of the min nodes. So this gives us 1, 3, 9, 11, 17 and 19. Okay, and these nodes form our initial clusters. Okay, so this is the tricky part of SSS star, in that it chooses the initial clusters in a reverse approach to what we usually take when we want to look at the number of possible strategies in a game tree. Mm-hmm. In SSS star, when you decide the initial clusters, you can straight away go ahead with the current strategy that we are following, because that is what is followed by SSS star all the time. If it's any other method and you are asked about the number of strategies, or even without mentioning which method to follow, you can safely assume that it's not SSS star and you can follow the previous strategy that we were using. Yeah. Okay, so these were the initial clusters. Let's verify the solution. So there are 6 initial clusters, and 1, 3, 9, 11, 17, 19 form the initial clusters. We just saw that. Now what we will do is we will apply the SSS star method, okay, and arrive at the final solution. Okay, and while we do that, we will also see how programmatically we could arrive at these initial clusters. So what we'll do for that is we'll use a priority queue. You might be familiar with a priority queue from the previous live sessions, right? So what we will do is we will follow this trend. Okay, we will follow the same nomenclature that we used in the previous when I previously mentioned in the previous question essentially. So this is the first level with the node labeled as A1. This will be B1, B2, B3 and so on and so forth. Okay, so let us fill in let us start the solution to our SSS star method. First what we will do is we will insert the root node, which is the A1 node. Okay, this will be assigned a status of live. Is my screen visible? Can you quickly confirm? I think there was a network issue at my end. Okay, thanks for confirming. Yes, so this will be assigned a status of live, which means that it hasn't been solved yet essentially, and then it will have a bound, let's call that infinity, and it will have a currently solved status or not, right, which sorry, that currently solved value or assigned value to this particular node, which will leave empty at this point of time. Okay, because this node is not yet solved. So is the nomenclature clear up till this point? Let's also mention the type of this node, which will be a max node. Okay, so we are at A1, which is a max node. It's a live node with a bound infinity, and it has currently not been solved, so it doesn't have any solved value given to it, which is why the last entry is blank. Okay, next what we will do is we will add its child or its children to the priority queue. Okay, the children of this A1 node are B1, B2 and B3, right? So let's add all of them. We'll pop A1 and we will add B1, this will be a min node, again live and the same bounds, and B2 and B3 as well. Okay, so this is what our queue looks like till now. After B1 we will look at C1. Remember, this was C1. Okay, so we will pop B1 and we will include C1, okay, which is the leftmost child of B1. So let's pop B1 and replace it with C1, which is a max node, again live and bound infinity and not yet solved, right? So the solved value is not there. Now we are at C1. After C1 we will, so this is what the queue looks like at this point of time. Next we will pop C1 and push the children of C1, which is D1 and D2. Okay, so D1 and D2. So let's replace this with D1 and D2. Okay, so this is what our queue looks like at this point of time. We have D1, D2, B2 and B3. Next what we will do is we will pop D1 and then add its leftmost child to the queue, which in our case happens to be E1. Okay, so we will add E1. E1 is a max node. It is also live, bound infinity, but it has a solved value of 64, right? This is E1. It has already been given a solved value of 64, right? So we know that it is solved, so we will change its status to solved. Okay, we will change its bound from infinity to 64 and then we will add it to the back of the queue. Okay, this has been solved now. So this is what our queue looks like at this point of time. We have D2 at the front, followed by B2, B3 and E1, which has been solved, at the bottom. Okay, we will proceed in a similar manner. Okay, so again we will pop D2, and instead of D2 we will add the leftmost child of D2, which is E3. Okay, so we will add E3, which will be a max node. It will be a live node with bound infinity and value of 69, right? Again, this is also a solved node. It already has its value. So we will change the status to solved, change the bound to 69, and we will add it to the queue. But can anyone tell me where will it be added? After E1 or before E1? That's right. And why is that? Max node, that is true. But why? Yeah, exactly. So this because this is a priority queue, not just a simple queue. The value it has is greater than 64, right? 69. So it will be assigned a place above E1. Okay. So this is what our queue looks like at this point of time. We have B2, B3 followed by E3 and E1. Yeah. Mm-hmm. Hmm. Um, so that will practically not happen, because usually when we make game trees, we uh, assume that the root node will always be a max node. Okay, so if you go in an interleaved manner of max followed by min followed by max, max followed by min followed by max followed by min followed by max again, you will always end up with a max tree, sorry, a max leaf nodes. Okay, so one meaning of 4-ply game tree is also that you are presenting your levels up to 4 plus 1. Okay, so let's have a look at a game tree once. Okay, so this was the first level, A, then B, then C, then D, and you stopped at E, right, which is 4 plus 1th or the 5th level. Okay, so you will always stop at a horizon nodes being max nodes. But what you can try to do is reverse this. Okay, change the order, assume the root node to be a min node, form a similar game tree, and see what changes occur in the algorithm as you try to solve it. Okay, does that sound good? Okay. Okay then, so this is where we were at. Now what we have to do is we have to we have to pop B2. Okay, and add the leftmost child of B2, which would be C3, right? The leftmost child of B2, sorry, where were we at? We were at B2, right? Yeah, so that's correct. This is C2 and this is C3. So we will pop B2, add C3, which is a max node, and it's live and its bound is infinity, and it doesn't have a solution yet. Okay, next we will pop C3 and we will add all the children of C3 over here. Sorry about that. So the children of C3 would be D5 and D6. So D5, which is a min node, it's live, and has a bound of infinity, and it's not been solved yet. Similarly, we have D6, again a min node, live, infinite bound, and not solved yet. Okay, so this is what our queue looks like at this point of time. Again, we'll pop D5 and add, what will we add? The leftmost child of D5, which happens to be E9. Okay, so this is a max node, live, infinity, and bound will be 17. Okay, again this has a value of 17, so we can label this as solved. Change the bound to 17 and then pop it and add it to the bottom of the priority queue. Okay, similarly we will then pop D6, which will then add E11, which will be a max node, again live, infinite bound, and a value of 13. Again it has a value, so we can label it as solved. Change the bound to 13, pop it, add it to the bottom of the priority queue. Now we have B3 at the top of the queue. If we proceed in a similar manner, we will arrive at the following configuration. When we will pop B3, we are going to add C5, right? So let's do that. We add C5, which is a max node, live, infinite, and no bound. When we pop C5, we will add its children, which are D9 and D10, which will be min and D10, which is minimum live node with an infinite bound and not solved yet. Again, when we expand D9 or pop D9, we will be adding E17, which will be a max node, live node, infinite bound, and a value of 62. Okay, again this is solved, so we can label this as solved. Change the bound, pop it, and add it to the priority queue over here. Okay, similarly when we pop D10, which value will be added? E19, right? E19, which is again a max node, live, infinite bound, and a value of 31, right? This is also solved, so we label it as solved. Change the bound to 31, again pop it and add it at its appropriate place in the priority queue. Okay, now we have arrived at a set of nodes that are solved. Okay, do you see a correlation between the set of nodes that we have and the initial clusters that we found? Any doubts till now? Okay, so I'm assuming that there are no doubts. That is great. So we have arrived at the initial clusters programmatically as well. Okay, aside the intuitive way that we saw in the previous question. Now these initial clusters are a part of our priority queue, and we will pop the topmost element next. Okay, so which is E3 in our case. Okay, now comes the tricky part of SSS star method. When we pop this E3, okay, which is this one, we will add its immediate next sibling node. Okay, sibling means brother or sister node, to the priority queue. Okay, so in our case that would be E4. Okay, so let's add that. So we will pop E3, add E4, which is again a max node, which is initially live. Okay, the bound will be same as the value of its sibling node, which was solved already, which was E3's value, which is 69. So bound will be 69 and value will be 68, which is the value of E4. Okay, now that we have encountered this situation in our priority queue, this we can label E4 as solved. Okay, and its bound is lesser than its greater than its value, so we can change the bound from 69 to 68. Okay, and we were supposed to pop it and again push it back in the priority queue, but we will see that it will occupy the same position that it currently has. Okay, so this is what the priority queue will look like. Because we solved it and we saw that the bound the solved value that this particular node had was lesser than its current bound, right, which is the maximum value it can attain. So we changed it to 68 because we know that this node has been solved. Okay, okay, now we know that E4 has been solved. Okay, let's revisit our game tree. E4 has been solved and there are no further siblings of E4, so we can say that its parent node D2 has also been solved. Okay, let's reflect that. So let's replace this with D2, which is a min node live, not live, it will be solved because all its children are solved. Its bound will be 68. We can leave this empty, or we can say that this is 68 and 68 as well. Okay, so this is what we are at right now, and we see that, let me erase all of this clutter. Okay, so we were at this position, right? We said that this has been solved with a value of 68. In SSS star method, the moment we encounter a min node that has been solved, okay, we can immediately say that its parent max node has also been solved. That is a property of the SSS star method. Why that is so, that you can find in the lecture videos. Okay, so now that we solved this T2, we can say that immediately its parent 68, right, which is this C1 node, has also been solved with value 68. Okay, now next we will look at we will try to follow a similar manner to what we just saw till now. Okay, so let's change our priority queue to reflect our changes. So we can say that C1, which is a max node, has been solved. Okay, now we will look at the sibling of C1, which would be C2. Okay, and we will recursively solve C2, okay, using SSS star method again to find that this also returns a value of 68 itself. Or let me verify that. Yes, that will be correct. Okay, there is a correction here. We should have removed E1 from here. Okay, because this has been solved. Once we solve C2, that we can also label as solved C2, which is max node, which has been solved with a value of 68. Okay, let's go back. So this has also been solved, and since this has been solved, we can say that so this will also get a value of 68, right? Because we have solved both C1 and C2, we can say that B1 has also been solved with a value of 68. Okay, so let's reflect that. Yeah, yeah, so C2 will be solved when we recursively apply the SSS star algorithm. Let me go back to the tree. So when we were examining C2, let's go back to the position where we had not solved C2. C2 is a sibling of C1, right? So this C2, this part of the game tree, consider this part to be a game tree of its own, and then apply SSS star algorithm from the beginning to just this part of the tree. Okay, and when you solve the whole SSS star algorithm for this part of the tree alone, you will find the solution of this to coming out to be 68. Okay, remember we will have a bound of 68, not infinity in this case. Okay, because C1 has been solved with a value of 68, so when we recursively solve this subtree, it will have a bound of 68 and not infinity. We choose the initial clusters again. Okay, we arrive at the initial clusters, we then pop out the topmost element of the priority queue, label it as solved, so on and so forth. Okay, I can show you the trace. Let me go to the trace. Yes, I will have the solution over here. So we were trying to solve C2. Let me see which portion of it was. Okay. Let us go to the position where we had C1 solved. Okay, so this was the status of the queue that we had. C1 solved, followed by E17, E19, E9 and E11. Okay. Then we add C2 node, okay, which is a max node, live node with a bound of 68. Okay, so this is what our queue looks like at that point of time. Once we pop C2, we will add the children of C2, which are D3 and D4. Okay, again with a bound of 68. So this is what our queue will look like: D3, D4 followed by E17, E19, E9 and E11. Okay, next we will pop D3 and add E5, right, which is a max node, live node, bound of 68 and a value of 90. Okay, I remember that it has a bound of 68, right? So when we label this E5 as solved, we will assign it a value of 68 and not 90. Okay, so this is how the 68 will get transferred to the final solution of the subtree. Does that kind of answer your question? Right. Exactly. Yeah, thanks for your question. That I think cleared doubts of some of your colleagues as well. Okay, so now we have solved C2 with solved value of 68. You can have a look at the trace later on. And because we have solved both C1 and C2, we can say that B1 has also been solved. And because B1 is a min node, which we solved, we can say immediately that its parent, max node, has also been solved with a value of 68. Okay, so you see what SSS star did. It pruned out this whole portion of the game tree. Okay, this whole portion was pruned out by SSS star. Whereas in alpha beta we still explored some of the nodes from this part of the tree. Okay, so like I was saying, SSS star goes one step ahead of alpha beta, sorry, not A star, alpha beta, in trying to make the solution more efficient. Diagrammatically, this is what our game tree would look like. So this infinity essentially means that this has been pruned out. Okay, so this was the SSS star algorithm. Any doubts here? Yeah. Mm-hmm. That is the property of SSS star. The moment one of the min nodes is being solved, we can immediately say that its parent max node has also been solved. Like I said, why that is so? For that I would refer you to the lecture videos. It's a property of the method. Yeah, exactly. Okay, let's go back to the question at hand and see what did the question exactly ask us after solving SSS star. Okay, so it asked us what are the horizon nodes that are assigned a solved status by SSS star, and if you go and look at the trace or our solution, you will see that the solved status would be including all the initial clusters, and along with that some other clusters that have been part of the solved solution, or the solved that have been given a solved status as we moved to the end of the method. Okay, it can easily be found when you look at the trace, so you can verify this yourself. See, you can notice here it has 1 3 9 11 and 17 19. Other than that, it also has 4 5 6 9. Okay, sorry, it also has 4 and 5 and 6. Okay, which were solved um, while we moved through um, the solution. Okay, you can verify this using the trace at your own leisure time. So this concludes the questions we had for today. Any doubts among the questions we discussed today? Mm-hmm. Mm-hmm. Sure. No problem. So again, this is also a property of the SSS star method, that when you have siblings of a particular solved node, okay, so let's say C1 was solved, okay, it has a sibling C2 which has not been solved yet. So you then try to, okay, sorry, yeah, so let's say C1 is solved, okay, C2 is not yet solved, okay. So what this will do is it will try to solve C2 recursively using the SSS star method on the subtree that is contained by the sibling C2, but the bound will be the solved value of the sibling node, which is C1. Okay. Remember, when we were trying to solve it initially, when we were trying to find the initial clusters, we applied a bound of infinity. But when we're trying to recursively solve this sibling node C2, we will apply a bound of 68, which is a solved value of its neighbor or brother or sister node, which is 68. Does that address your query? Yeah, same thing applied at any step. Okay, anything else? Okay, if not, then that's great. Um Okay, so I think we can end the session here. Okay, all the best for your upcoming assignment. Have a good evening, and let's meet next week.